Now let us examine the technical details of PCA. So PCA relies on the covariance matrix. And you should have known variance very well, where variance measures the spread of data points around their center of mass, which is a mean. Basically, measures the spread with respect to the mean. And the covariance also measures the spread of data points with respect to mean. For variance, which is a concept for a scalar, so it measures the deviation from the mean for points in one dimension. In contrast, covariance measures how much each of the dimensions vary from the mean with respect to each other for multivariate vectors. So basically, a covariance is measured between two dimensions of a multivariate vector. And what covariance trying to measure is the relationship between two dimensions. And you can think of the variance as basically a degenerated version of covariance, which is the covariance between one dimension, that is between the variable and its self. So the covariance between one variable and its self is variance. So here is illustration of a positive covariance between two variables x and y. If x and y if they have positive variance covariance, then both dimensions will increase or decrease together as a general trend. Right? So if x and y has negative covariance, then when one increase, the other will decrease. Right? So that is a negative covariance, and this is a positive covariance. Right? So basically, covariance capture the relationships between dimensions in high dimensional data sets. And the scatter matrix is basically a sample-based estimation of the covariance matrix. Here, we use I to index the sample, that is, there are n samples, and G and K to index the variable. So this is the J case element of scatter matrix X. It is computed as the variance of J, variable J, from with respect to variable K. So this is the mean, the sample mean of the J's variable. And this is the sample mean of the K's variable. And this is I is a sample index. So basically, this SJK measures the covariance between the variable J and K. J and K. Therefore, when we have uncorrelated variables, their covariance will be 0. And if we have a diagonal covariance matrix, which diagonal means there's all the off-diagonal elements are 0, and we have only non-zeros along the diagonal. Therefore, in this case, all the variables are uncorrelated, because the diagonal is basically the variance of the variable with respect to itself. It is basically the variances for individual variables. And now let us using the definition that PCA maximizes the variance captured in the projection to derive PCA. We start from the scatter matrix for the input, which defined earlier. So, but this is a input scatter matrix. So what will be the scatter matrix for the projections? Suppose we have a projection matrix U. So the answer is this is the scatter matrix for the projections using projection matrix U. So we look at the PCA's principal components, the directions, one by one. Let's look at the first PC, the first direction. This first direction will maximize the variance in the projected space. That is this y projected by the first direction, first projection u1. So we want to maximize the variation of y. So the variation of y is defined in this way. So this is a mean of y, and this is the ith sample. So we substitute the projection u1 transpose times x into y, then this is what we have. Right? Then you can recognize that because u1 and u1, they are not indexed by x, so you can pull this out to here, right? So and pull this out is not, then in the middle, what you left with is actually the input scatter matrix S, right? So therefore, the variance of y is u1 transpose times the input scatter matrix times u1, right? So that is the variance of the output after projection. So now we want to solve for this. We want to learn this direction, right? So we want to find the first direction. And how to find it? We solve for u1 through a Lagrange multiplier method. That is to solve it with a unit norm constraint optimization. This is a unit norm constraint which constrain u1 to have norm 1. And this is the variance we want to maximize. Therefore, we form this Lagrange multiplier optimization problem. This is a variance and this is a constraint. And this is a regularization parameter or Lagrange multiplier. And then to optimize it, we take a gradient with respect to u1. So this is what we have through some calculus. This is what we have. And then we set this gradient to 0 and rearrange. This is what we have. And from linear algebra, this is basically the eigenvalue problem. And this will give us the first principal component. However, we know that for eigen decomposition problem, there are many solutions, right? So there are multiple eigenvalues. So which one should we choose as the first PC, the first principal component? By the way, when we choose a particular eigenvalue, there's a matching eigenvector, and this eigenvector will be our principal component. So which one to choose? The answer is because go back to our objective. We want to capture the most variance. And now let's look at what is the variance. The variance of y, we know it is u times u transpose times s times u. So now let us substitute su here with lambda 1u, right? So this is what we have. And because u has uninorm over here, it has uninorm, therefore ut times 1, the norm is 1, so what we have is lambda. Therefore, the variance of y is simply lambda. Lambda is our eigenvalue. And because we want to have the maximum variance, therefore, we take the maximum, the largest eigenvalue. And then our first PC will be the eigenvector corresponding to the largest eigenvalue. So now let's look at the full PCA solution. And just now we have the first PC, but for further directions, how we obtain the other PCs. So basically, the other further directions, they should be orthogonal to the first PC and all previous PCs. Orthogonal means uncorrelated. And the solution is basically the top k eigenvectors of S. And here, the eigenvectors are basically the basis functions define the direction in the transformed space. And they are called the principal components, or PCs. And the eigenvalue is the variance captured respectively by each eigenvector or each PC. So here's the question. I don't know whether you have wondered just now. For U1, what if we do not have that unit norm constraint? If we do not have this uniform norm constraint, if we try to maximize the variance directly, what are we going to get? So you can pause the video and think about it, right? So what is the maximum we are going to get? What is for this formulation without the constraint? The answer is that we are going to get a trivial solution, because to maximize this one, if you do not put any constraint on u, the solution is that you just have infinite value for every element in U. Then basically we will have infinite variance, but it doesn't help us because it is a trivial solution with projection vector with infinity in each element. Another question is that for the further directions, what if we do not require them to be orthogonal to the previous eigenvectors? This is more difficult because we didn't go through the steps to obtain the following pieces or directions. But if you are interested, you are encouraged to go through the process and try to learn it, right? So the answer is, if we do not constrain the remaining vectors, remaining projection to be orthogonal, then basically we still maximize the variance, then basically we will have the same U1, the same first PC. And you basically have duplicate pieces, and again, it's useless. So we have used one formulation with maximum variance for PCA. Actually, there's another formulation where we can aim to minimize the reconstruction error in an approximation problem. You can derive the same PCA. So let's now consider just the first PC, the first principal components with a projection vector U. and we assume that the data have zero mean and already centered, then our previous formulation with maximum variance capturing, which will give us a vector so that it captures the maximum variance in the data, right? So with zero mean, the mu is zero. So this is what we have, right? This X is the data matrix, right? So that is another form of the variance, right, for the first PC. And it is indicated by this blue line over here, right? So basically, the variance is indicated by the length of this blue line over here. And so this X is the original data point. And for the minimum reconstruction error approach, here is a typo, right? So you need to be at the top, I fix it. And the first PC, suppose we take the minimum reconstruction error approach, then the first PC will be a vector that will lead to the minimum mean square error reconstruction, right? So then this is the objective function, and this is basically the reconstruction, right? So this is a projection y, and this is the reconstruction. And then when you subtract it from the original data, you have the error, right? So suppose our first vector aim to find a one-dimensional projection, minimize the projection error, right? So find a u, then that will give by this, basically this reconstruction error is indicated by this green line over here. So that is basically the error, right? So that is the error. And so here you can see a form of the triangle, and we know the blue square plus the length, right? You talk about the length, blue square plus green square equals to the black square, right? So that is a simple geometry formula over here. And basically, the black is original data point, so it is fixed, right? It is just the data. Therefore, when you rotate this u along the origin, right? So if you rotate it, for example, to here, right? So then basically you project it, right? So then if we want to, when we try to maximize blue square, right? So that is a variance is a square over here. When we try to maximize the blue, this is equivalent to minimize green, right? So when you try to maximize blue, because this is fixed, right? So then black is fixed, is equivalent to minimize green, right? So therefore, maximize the variance is equivalent to minimize the mean square error of reconstruction. So that is two equivalent way to derive PCA, and they obtain the same solution of eigenvectors. Finally, another question is how many, we know there's a hyperparameter k, right? So how many PCs shall we keep in practice? So actually, in fact, we can pick, if it's for dimensionality reduction, right? We can pick based on the percentage of variance captured or lost, right? So we know the variance captured is a variance of the projected data. And typically, if we specify a percentage, let's say we want to keep 95% of the total variance, right? So we want to keep 95% of the total variance. Then we just pick the smallest k that can explain at least 95% of the total variance, right? So the summation of all the eigenvalues, EV represents is a short form for eigenvalue. Summation of all the eigenvalues is simply the total variance in the original data. And the summation of the first k eigenvalues is the variance captured by the first k eigenvectors. So then you divide it by the total, you get the ratio or the percentage. And in practice, you can also look for an elbow in the scree plot, which is a plot of the percentage of variance captured by each PC, or equivalently, the eigenvalue. So this is when you do not have a strong preference, this is how to determine the number of PCs. But for example, in visualization, right? So in the example we show in the earlier, in visualizations is constrained by the application, right? So because our human eyes, we can only observe 2D or 3D space. Therefore, we typically pick k equal to 2 or 3 if our task is visualization. So that finish our introduction to PCA. And in the next session, we'll move on to another fundamental problem of clustering.